Alright, so at this point, you've now looked at how you can add things in series and parallel, and you've used Ohm's law and the resistor rules to try to figure out, does that increase current or decrease current? Where's the energy going? And we wanted you to have a chance to explore that. Those rules are important, and you'll use them in more advanced classes. But on a complex circuit like this one here that I use in my AP Physics 2 class, they start to get very confusing. This is a circuit that has two batteries in it. And this battery is trying to push current in one direction, this battery is trying to push it in another. How do you handle things like that? And how do you handle circuits that have things other than resistors in them? Well, the person who gave us really good tools for that type of situation was a German scientist in the 1850s named Gustav Kirchhoff. And his rules focus more on energy. What happens to a charge if it's sitting in a circuit and a battery grabs it and throws it up to a higher potential energy? How does it go through the circuit and get back to where it started? How do currents that flow into a place, where do they go? Like two rivers flowing into where rivers merge. Where does the current go? Kirchhoff was thinking like that, and it gives another powerful way of analyzing circuits. I'm going to try to demonstrate in this video the physics phenomenon called Kirchhoff's loop rule, which is a way of keeping track of how energy and voltage divide in a circuit. It's actually pretty straightforward, and I hope if you see this applied with real lab equipment, you'll understand the rationality. So our circuit's going to be really simple. It's going to have a battery, and its symbol for the battery is this thing right here. It's going to have a 100 ohm resistor with the color code brown, black, brown. And it's going to have a 1000 ohm resistor with the color code brown, black, red. So what we're going to do is wire up our circuit as that diagram shows. We're going to get the three voltages that are interesting: the voltage across the 1000, the voltage across the 100, and the voltage across the battery. So on my breadboard here, I'm going to put the foot of the 1000 into its own row of holes, and the other foot into a second row. Make sure they're both seated real well. Then I'm going to take the foot of the 100 and put it in the same row as one of the 1000, and then into a different row. Make sure everybody's seated real nice. And then I'm going to put the battery leads, I'm going to hook them up to the resistors. So electricity should be flowing using the standard direction of current from the positive side of the battery to the 1000 to the 100 back to the battery. And let's check that we've got voltages. Across the battery, we appear to have a voltage of 1.49. The negative sign is because I have the leads reversed from what we'd expect. So I'll write that down as V is 1.49. We'll check across the 1000 ohm resistor. We can see that this stabilizes around 1.36. And we'll check across the 100 ohm resistor. We can see it stabilizes at 0.13. So it's interesting here. There's a couple things we can note from our pattern, which is we've got about a factor of 10 times the the voltage in the 1000 ohm resistor than in the 100 ohm resistor. And that is because we've got 10 times the resistance. So what we're seeing is that in terms of voltages being used up, the 1000 ohm resistor appears to be using up more of the voltage than the 100 ohm. And that's a pattern that we'd expect. But there's another pattern that's a little more subtle, and that's what Kirchhoff's loop rule is meant to show us. Kirchhoff's loop rule basically says, if you're a charge where I have this X, and you take a walk around a circuit, you should get back to the voltage you started with. So let's take a little walk. If we go across the battery, we're getting a voltage of plus 1.49 volts. We're going to then continue across this resistor, and then we fall down minus 1.36 volts. So if you do a little bit of math, that means we're now at 0.13 volts. And guess what this one takes away? This one takes away minus 0.13 volts. So we get back to exactly what we started at. Now why is this? Well, if this is a coulomb of charge, we can essentially be talking about potential energy. This would be 1.49 joules to get to the top, and then minus 1.36 joules, minus 0.13 joules. I think the best way to look at it is if you went on a hike up a mountain. You parked your car at the base, you went up and got 1.49 joules of potential energy, and then you took a scenic route back down. You went part of the way down, and then you went the full way down. But your car's still in the place where you put it, at the base. So if you go all the way around, you have to get back to the energy you started with. So Kirchhoff's loop rule is essentially a statement that energy is conserved. The purpose of this video is going to be to talk about how current divides in a multi-branch circuit. I have here a circuit that's a little more complicated than previous ones you've seen. It's not a series or a parallel. It's kind of a combination of both. Let me show you. If we take out paths that current could go by, it could leave the positive terminal, go through the 100, go down through the 4700 in this meter, through this meter in the 22, and get back to where it started. However, it could also use that outer branch. Could go through the 100, skip the 4700, go through the 1000 and this meter, then it has to go back through that 22 again before it gets back home. So in a very real sense, the 100 and the 22 are different than the other two resistors. The 4700 and the 1000 are in parallel with each other, but the 100 and the 22 are in series with both of them and each other. So what's the relationship between these currents? I think it's worth checking, and that will help us understand Kirchhoff's junction rule, which is one of the most powerful tools in helping us understand circuits. So because we're measuring currents, we actually have to break the circuit because you measure current through. So I'm going to pull out the 4700. I'm going to disconnect it from the top of the circuit. I'm going to hook one of the yellow wires where it used to be, hook another up to it. So now if I put the ammeter in, I can measure current through it. We'll flip that so it's in the right direction. We get a current through the 4700 ohm resistor of 276 microamps. So I'll write that down. I already forgot it. 276. So 276 mu amps. And now we'll go through the 1000, so we have to put the circuit back together. 4700 goes back like it used to be. And we'll pull the 1000 out. Put a yellow wire where it should be, yellow wire to it. will get its current 1211 microamps. So now all that remains is to get the current through the bottom here and through the 22 ohm resistor. So we'll put the 1000 back together. Make sure everybody's seated well. We'll pull off the 22. Give it a new home. Yellow wire up to it. Yellow wire up to these two guys. Excuse me. And we'll get the current through the 22. We get 1431. So, if we look, there's a fairly clear relationship between these currents. If we simply add them together, 1211, 276, we should get something very, very close. So we should be getting 1487 microamps. We're getting 1431. These are very, very small currents, so the meter's not super accurate. But I think it makes intuitive sense that the current through the entire circuit, which represented by the 22 ohm resistor, would be the sum of the currents through the two separate branches. So that brings us to the definition of Kirchhoff's junction rule. He says if you have a junction, like right here, and you have currents coming into it, you have to have the same current going out of it. It's a statement of conservation of charge. Charge doesn't get lost. So we've got 1450-ish milliamps coming in through these two branches. We've got 1450-ish microamps coming out. No charge is lost in there.